Good evening, everybody. Welcome back at Studium Generale after a week full of celebrations and lots of people with a cold at home. But don't be afraid, we do have recordings of this lecture. So we'll send you a link afterwards. You can send it around to anybody who wasn't here, or you can watch things back. Welcome at this lecture of Studium Generale. I'm Rob van Duin, head of the Office of Studium Generale and program maker. And when I came across the research of the speaker of tonight, I have to take off my glasses, Professor Christian Keizers, I got really curious about the research, and I found it very interesting to look at the empathic brain, and in this case across species. Because we do wonder, where do we find our empathy? Is this selfish, or are we indeed social beings that find the need to help? It's interesting to look at it in a philosophical way, which is actually the questions you ask yourself, I think, more often when you do your research. But it's also interesting to look into our brain to see where does this empathy take place. Is there some area in the brain where we can see things lightening up when we feel the urge to help somebody, or to understand somebody, or feel somebody else's pain? And that's the research that Christian Keizers does. He will talk for about an hour, after which there's still time for some questions. He is head of the Social Brain Lab in the Netherlands, interesting lab, Institute for Neuroscience, and full professor for social neuroscience at the University of Amsterdam. Please welcome Professor Christian Keizers.
Thank you so much for having me, Rob, and thank you all for being here in the evening to listen to 1 hour of my talk. Now, the big question that really fascinates me is why the state and the emotions of other people influence us so strongly. So if you have a look at this young Ukrainian boy that just lost his family, if you look at his eyes, at his tears, at his gaping mouth, I think that most of you cannot help but to become emotional. Most of you cannot help but to feel part of his distress. And in addition to that, some of us also start to really feel an urge to do something to help people like him. And what really intrigues me is, why is it that we don't just understand what happens to this boy, but we start to feel distressed ourselves? What is it that connects my state to your state in such a strong way? Now, in this talk, what I'll start with is having a look at what happens in the human brain when we witness the state of other individuals. Then I'll go on to ask whether animals actually have a similar sensitivity to what happens to other animals, to then ask whether the sharing of the emotions of others really influences what we're willing to do for others. And at the end, I'll ask a bit whether empathy or this feeling is something that just happens to us, or whether it is something that we kind of decide whether we want to feel it or not. So let's start with what happens in our brain while we witness the states of others. And for me, this research started not actually looking at humans, but looking at monkeys, and simply looking at what happens while monkeys witness the actions of other beings. Now, at this point, we were recording from the premotor cortex, which is this part that you see here in blue. Whoop, here we are. There's a delay, so it's a bit challenging here. So this part of the brain, when we started this research, was thought to be exclusively there to program the monkey's own actions. So if you record from neurons in that part of the brain, what you notice is that each neuron has a job that it's doing. Some of them program grasping, and whenever you'd activate them electrically as well, you'd see that the monkey will start to grasp things around him. But what we observed, and that wasn't meant to be in that part of the brain, is that the same neurons were actually responding while the monkey wasn't doing anything, but observing other individuals perform similar actions. And if you have a neuron that's involved in grasping with the monkey does it, you see that it responds whether I grasp with my hand or with my lips. And what I'm going to show you is a little movie in which you'll see more or less what it was like to be in the lab. You'll see the monkey grasping a piece of food first, and then you'll hear the firing of one of the neurons in the premotor cortex. And then you can listen again to the firing while the monkey isn't doing anything anymore, but is witnessing me perform a similar action. So this is the motor part, where the monkey is grasping, and this is while the monkey is just observing me. And what made these neurons so interesting to us was that for the first time we were seeing that something that you see other people do doesn't just recruit something in your visual cortex that allows you to physically see it, but your brain transforms it into the language of your own actions. So with neurons like that, in a way, if you'd see me, for instance, grasp my bottle and drink from it, nice. You wouldn't just see me drink, you would in a way internally generate what it feels like to drink yourself. So something stops to be visual and stops to be something personal, something that you have experience with. Now you might wonder, I'm not a monkey, so how do you know that the same thing happens in me? That would be a perfectly legitimate remark. What we can do in humans, we don't have the ability to listen to the activity of individual neurons, but what we can do is take one of you, put you in a scanner, ask you to perform certain actions like scooping soup out of a bowl or drinking from a glass, and afterwards I would see what part of the brain are active when you do something yourself here in red. And then I can also show you simply movies of other people performing the corresponding actions, like drinking from a glass or scooping soup out of a bowl. And what you would find there is activity in these blue regions. And if you overlap them and show the overlap in white, what you see is that part of your own motor system gets reactivated while you're simply passively observing what other people are doing. What you may notice is that some parts, the part here in white, are reactivated as if you'd be doing something similar, but other regions here that remain exclusively red are only active when you do something yourself. So that would involve the primary motor cortex that directly descends into your body and your muscles. Because if you would activate that part as well, then you would be gesticulating and walking around right now with me, which would not be ideal in a lecture. So in a way, your brain has this ability to balance the two things. It reactivates part of your motor system as if you were planning to do something similar, but at the same time it suppresses the primary motor cortex so that you don't compulsively imitate everything I'm doing. But what this showed us, in a way, is that what we observed at the level of single neurons in the monkey is kind of mirrored in the human brain, at least at the level of brain regions. And by working with both monkeys and humans, we have, in a way, the advantage of both. We can see the general picture in humans, and we know that if we zoom into the same brain regions in the monkey, we see that it's not just the brain region that's active in both cases, because that could be due to individual neurons, with some of them only doing my own actions and some only doing yours without the real merging. But we know that if we zoom into the individual neurons, you see that the very neuron you would use for your own actions gets reactivated when you witness the actions of others. And for me, there was a real epiphany, because for the first time we got this feeling that what we call normally empathy, the sense that we can feel with other people, is something that is really wired into our brain to the degree where we really activate very personal states, like our own actions, where we simply witness what other people are doing. Now, of course, in many cases, the thing you empathize with is not an action like grasping a bottle, but we typically think of emotions and sensations. And I remember at some point I was discussing these motor findings with my wife. We lead the lab together, and she was cooking, so she was cutting an onion, and I distracted her so much with the science we do together that I suddenly saw how the knife stopped to cut through the onion and started to really slice into her finger, with the skin kind of parting a bit and some blood coming out. And I remember how I really had to shake my own finger because the sensation was so strong in my own body, a bit as if I had cut myself. So we figured, gee, perhaps what we had observed in the motor system is not just true for actions, and we have something similar for sensations like pain. So we decided, let's try to do an experiment in humans, and we decided to put people in the scanner, but not to cut their fingers, because then we can only get 10 trials, and we need more than that for good data. So what we did instead was to simply touch them on their legs. So for 10 seconds we touch one leg, then we switch to the other one. From that we can measure the part of the brain that encode the sensation of touch on your own body. And the main region you see here is what is called the secondary somatosensory cortex, which is just close to your Sylvian fissure. So I can also open the Sylvian fissure for you here, and you see how the secondary somatosensory cortex kind of goes into this Sylvian fissure. Now, the second part of the experiment involved showing people these beautiful legs being touched, and please don't laugh because they're my legs. But by doing that, we could localize regions that are simply active when you see someone else's bodily sensations. And we found this blue region here with again an overlap between feeling touch on your own body and seeing someone else being touched, which was starting to point at the fact that we might be looking at a more general principle where if I see the actions of others, I activate my own actions. If I see the sensations of others, I activate my own sensations. And again, we didn't find a lot of activity during observation in the very early part of your brain that processes touch. So they remain exclusively involved in your own touch. But these higher brain regions, like the secondary somatosensory cortex, become an area where your touch and my touch start to overlap, allowing you to both feel what I feel and not be confused about who is actually being touched. But still, we're not really looking at emotions here. It's still a sensation. So we figured, how could we try to understand if people really share the emotions of others? Now, these experiments are a little bit more difficult because I can put you in a scanner and ask you to be happy for me for 10 seconds and then to stop. But that's not going to work very well. So we figured, what could we do? Well, we put people in the scanner and put an anesthesia mask on their face. And I figured, why do I get an anesthesia mask? But we just told them to wait a little bit, that they were going to find out soon enough. And then what we started to do was to put really unpleasant smells through that anesthesia mask. And that worked pretty well. So we had to take one subject out because he started vomiting in the scanner. But for the other ones, we could get very nicely and repeatedly a strong emotion of visceral, really disgust, while we can localize the activity in the brain. And then we had another condition in which they were simply watching someone else taste something and look really disgusted. And what we observed was that when you feel yourself disgust, you see activity in this region here that's inside a bit more of the brain, that's called the insula, and it's really involved in your own bodily sensations. When you observe the disgust of others, you reactivate part of this region, and again we have this overlap at the level of brain region. Now what's interesting is sometimes neurosurgeons put electrodes in that part of the brain before they remove a part that they suspect is causing epilepsy. But when they stimulate that part of the brain, what happens is that people really feel, for instance, their stomach contract. Some of them start to taste strange tastes in their mouth, and some of them start to smell weird things out there. So what that shows us is that while you witness the emotions of others, the brain regions you activate are not just abstract cognitive brain regions that tell you, I understand that the person is disgusted. No, you actually recruit these more bodily, visceral sensations that you normally associate with the matching facial expression. Now, the other emotion that we found to be reliably usable in the lab is pain, because what we can do, we can just come in the scanner room and whack you with a ruler. That will induce pain, and we can show you the pain of other individuals in a movie. And what you see when you look there for an overlap is you find again the anterior insula. So unfortunately, it's not the case that in the brain, when you see activity in a particular brain region, you know exactly what people feel, because it could be pain, it could be disgust. But we also find activity in a bunch of other brain regions that I'm going to come to. But before that, I wanted to show you briefly these results that we again get from epileptic patients. So these are patients that come to their surgeon saying that they have so many epileptic fits that their life is not normal anymore. So they ask surgeons to intervene and remove the source of the epilepsy. And before the surgeon does that, they sometimes put electrodes in the brain to measure where exactly the epilepsy starts. And that allows us sometimes to get something we normally only get from monkeys, which is the ability to directly record from the electrical activity. And what you see there is that in all these parts that have the black dots in the insula, we could know by just measuring the level of electric activity how much pain you would perceive in someone else. So we show you different levels of pain. We read out the activity there, and I can predict whether you're going to tell me that the other person is feeling a lot of pain or a little bit of pain or no pain at all. Now, the other brain region that's really involved in pain, and that will come back in this lecture more often, is the anterior cingulate cortex. So that is really more specifically involved in pain. Sometimes when you have a chronic pain surgeon, chronic pain patient, surgeons actually lesion that part of the brain, and the person then is no longer really bothered by the pain. So it's really involved in your level of sufferance triggered by pain. And another region we see as well is the somatosensory cortex here in humans. Now, with all of these findings, people were starting to really speculate that if it is true that the brain activates your own pain when you witness the pain of others, well, then we know why you care about what happens to others, because basically you care about what happens to them, because if they're in pain, you're in pain. And that means what Adam Smith was saying already in the 1700s, that in a way we care about what we do to other people, because we don't like to feel the pain that they feel. Now, this is a speculation, and even with the result I've shown you, it remains a speculation for mainly two reasons. First of all, for the case of pain, I haven't shown you yet that it's really the same neurons involved in your own pain that get reactivated when you witness the pain of others. And above all, I haven't shown you yet that if I were to suppress that activity, you would no longer care about the pain of others. And that is something that scientifically we really need to do, because if you don't do that, you do not understand really how a mechanism works. So if, for instance, you were coming down from Mars and you were trying to understand how these weird cars reduce their speed, you might observe cars and you figure, oh, each time the red light in the back turns on, the car decelerates. So surely it must be the red light that somehow through photonic engine is slowing down the car. If that would be your conclusion, of course you would be wrong, because the red light in the back does not slow down the car. And the best way to check your hypothesis would be to take a hammer, break the red light, and see if the car would still slow down. That's how in neuroscience we really test these hypotheses, but the problem is that we cannot do that in humans, because in humans, people don't like you to break their brain to check whether something is mechanistic. So to be able to really go from speculation to a real understanding of empathy and your willingness to help others, we really need to have animal models in which we can test these things. And what I'm going to present to you now is our effort to try to see whether animals have a similar system and whether we can therefore go deeper and really understand the mechanisms of empathy. So before we get into the work with mice and with rats, we have to ask ourselves a bit, what do we actually mean with empathy? Because we often use empathy in everyday language in a relatively all-encompassing way. Psychology, though, decomposes empathy into some different and important components. So if you think about what happens while you witness this poor Ukrainian boy, the first thing that may happen is that you just start to feel some distress yourself. That per se is what we call emotional contagion, which means that if you're around someone that's distressed, you get distressed. If you're around happy people, you kind of get more happy. The next level is what we call empathy proper, which means that not only do you now feel the distress, but you're actually aware of the fact that it's not really your distress. This is a distress that you have on behalf of someone else. So this requires a layer kind of cognitive attribution of now the bad feeling that you have onto someone else. And the next step would be prosocial behavior. That means the motivation to really do something for the other individual. Now, as we go from humans to animals, one level, which is what we call kind of an empathy proper, is going to be difficult to assess, because that would need us to know what the animal knows, which is very difficult to do without language. But I'm going to try to convince you that the other two things we can study in animals. We can see whether they experience emotional contagion, and we can see whether they're willing to do things to help others. Now let's start with emotional contagion. So the design we use there that works very well with both mice and with rats involves to put two animals face to face. They're separated by a little wall that is transparent and has little holes in them, so they can exactly happen, they can smell, they can hear what the other one does. And then what we do is we startle one of the two by giving them a little shock on the electric grid. This is not really painful, but it is, if you've never felt electricity. I still remember the first time that I put my fingers in the plug. It's a weird feeling that's quite scary. So what you do with that is you scare one of the two, the demonstrator, and what rodents do when they're scared is that they stop to move. They do what is called freezing. They completely stop to move. that's very adaptive, because if you have a cat that's trying to eat you and you completely stop to move, you really reduce the likelihood of being detected. So of course the demonstrator that gets the foot shock does a lot of freezing. So here what you see is how much time they spend in this position where they don't move at all. Before there's any shocks, which we call the baseline, they don't freeze. And then as soon as you give them these 5 little foot shocks, they start to freeze a lot, almost 100% of the time. But what's really interesting is what happens to the observer. The observer doesn't get any foot shock, doesn't have any reason to be scared, but what we observe is that they actually start to freeze as well, as if they were scared at this point, showing us that not only humans care about the state of the other, but also the rat here is being influenced by the state of the other. Now, of course, rats have never experienced foot shocks before this experiment, so it's probably a little bit difficult for the observer to actually relate to what is happening to the other one. So we figured, how would this change if a couple of days before the main experiment, we give the observer as well a couple of these little foot shocks so that they know what it feels like and how they themselves react to this. And if you do that, and then afterwards let them observe another animal get foot shock, you see that now they really respond as much as the demonstrator. So nothing is happening to them directly, and at the moment where you put them into the experiment, they also don't freeze. So it's not like they got scared of these boxes, but as soon as they witness the other animal getting the shock and freezing, they start to do the same. So what this really shows us is that we now have an experimental design in which we can measure how much one animal is influenced by what happens to the other one. Now you might wonder, I'm going to skip that, you might wonder whether what we here see in the animal is anything like what you experience when you see someone else get a shock. And I think this is a really fascinating question. Unfortunately, we'll never be able to really know what the animal, the observer, is feeling. But as neuroscientists, what we can do is we can look in the brain of the humans, we can look in the brain of the animal, and we can ask ourselves, do the two brains react in similar ways? Because if the two brains look similar when they witness someone else getting a shock, then we have some indications that there might be something similar happening. So in the humans, I told you about the importance of this region here in the cingulate. And what we can now do is measure the brain activity in the rodents while they're experiencing something similar to see another one getting these foot shocks. Now, we don't put rats in MRI scanners for the fact that in a human you can explain them it's going to be very loud, but don't worry, and this isn't bad for you. If we put a rat in something as loud as an MRI, they're not going to care a lot about what happens to other animals. But we have a relatively new technology that is involves ultrasound imaging, in which we can basically measure something very similar, which is localized blood flow, and ask now, in a completely silent environment, what happens to the brain of the observer. And when we do that, we basically see that in the rat, we see activity in the anterior cingulate in exactly the equivalent region to where we see the activity in humans. So two animals that evolved separately for 80 million years activate the same part of the brain involved in their own pain when they witness the pain of another individual. So now we have some indication that actually what we see in the rat or in the mouse can have some relevance to what happens in the human brain. And now we can start to ask whether this sharing, this activation of your own pain, is really important for the way that you relate to the pain of others. So the first experiment we did is actually quite simple. It involved taking the equivalent region in the rodent brain, here in the cingulate area 24, and now we can have two groups of animals, one in which we simply inject saline, which doesn't do anything to the brain in that part, and another group in which we inject muscimol, which is an agonist of an inhibitor in neurotransmitter GABA-A, and basically it for about half an hour deactivates the cingulate. Then we can repeat our experiment and ask whether the observer's reaction to the pain of the other would be modified if you inhibit the part of the brain that we see important in humans. So here you first see again that the observer freezes about 80%, so a lot, if you just inject saline. And now if you deactivate this region, the observer basically stops to freeze. So now they see the other guy get the foot shock, but don't freeze at all anymore, simply by deactivating the region that we had seen to be involved in humans. Now you might wonder at that point, what is it exactly that we have suppressed? Is it that the rat can now no longer feel fear or perhaps cannot freeze anymore? Or is it that we've really interfered with something more like empathy, this social phenomena? Well, there is a simple way that you can check that, which is the fact that we know that if you pair for a couple of times a foot shock with a simple tone, like beep, you can do that in humans, you can do that in the animal, you see that afterwards, if you just play back the beep tone, they get scared. And that's exactly what we see. If we just play back the beep tone later on, these rats freeze as well 80%. But now, if you deactivate the cingulate, there's no reduction in the freezing. So it's not like without the cingulate they can no longer be scared. It's just that they no longer get scared by seeing someone else being in pain and being scared. So indeed we have one of the critical links here between your state and mine, and we can finally show that it's really necessary for this phenomenon. Something interesting that we observed is that if you inject muscimol in the cingulate of the observer no longer really cares. What is interesting is that we see that this also a little bit makes the demonstrator less scared. So now the demonstrator still gets the foot shock, looks around and sees nobody else seems to be scared here, then they actually get less scared by their own foot shocks. So in a way, what happens here between the two animals, it's not just that the one that gets the foot shock sends basically the fear to the other animal. There's also something coming back the other way, where if the other one stays very calm, in a way your assessment of the situation becomes less stressful than if you see that the other one is freaking out as well. And that's something that my wife always uses. If I'm getting a flu and I'm complaining, being miserable, she just ignores me completely and hopes that it will make me feel better. I'm not sure it works for me, but the facts speak for it. Now, the next question we had is, okay, we see that this brain region is really important, but what would happen if we zoom in? Would we really see that it's the pain neurons specifically that get reactivated when you witness the pain of others? So what we can do there is we can put electrodes into the cingulate of the animal, where we can listen in on the activity of individual neurons, and now we can have two conditions. We can have one condition in which we shine a CO2 laser on the paw of the animal that creates a sensation of heat that is a little bit painful. If you do that, you see that the neurons in this region respond quite robustly. That's what you see here. It lasts for about 2-3 seconds, which is also, when I shine it on my own hand, it's about as long as the pain sensation lasts. If I reduce the laser intensity to the point where it feels warm but no longer painful, the activity in the rat cingulate flattens down. So it's not about heat, it's really about pain here. What is interesting is if I record from the same neurons while nothing happens to the implanted animal, but to his friend on the other side, I find a response that is just as strong in these neurons as when the animal is in pain itself. If I reduce a bit the intensity of the foot shock, where it's still painful for the demonstrator but a bit less, the response is a little bit lower. And if I go down all the way, the response is gone. So it's not just that the animal realizes there's something weird happening, it gets this quantitative feeling for how much distress the other one is feeling, and it's transforming it directly into its own pain representation. This is true for about 10% of the neurons in this brain region. That's important to keep in mind. So 90% of the pain neuron of this rat do not care at all about what happens to the other rat. But there is a proportion of them, which we call mirror neurons, that have this ability to really translate the pain of others into its own pain. We don't know yet what makes this 10% different from the other ones, but we know that there is this kind of partial overlap that allows the animal both to, in a way, get influenced by the state of others and at the same time still be able to differentiate whether they're in pain or someone else is in pain. Again, if we just play back this tone that they have learned to fear because we've paired it with shocks in the past, there's no response here. So it's not like it responds to anything that's salient, it's really the pain of others that gets transformed here empathically into the animal's own pain. Now at this point you might wonder, why does a rat care about the state of another rat? So in humans, we have this tendency to think that empathy or sharing emotions is something that is very intimately tied to prosociality. So there is entire theories from Frans de Waal, for instance, that the reason why we empathize is that as mammals, our parents really need to care about the distress of their kids, otherwise we wouldn't survive, and we just somehow enlarge this benevolence to the other people around us. I think when we look at the rats, there might be a much simpler explanation for why they care about the state of others. And this is a scene out of my kitchen in Amsterdam. I don't know what the situation is here in Maastricht, but in Amsterdam every house seems to have mice in them. And what is happening here is that my cat also enters the room, and one of the two mice can see my cat directly. So they, of course, will freeze, and that's good for them because that means that the cat cannot really see or hear them in the dark, and they typically, somewhat annoyingly for me, survive. But what happens to the other one? The other one cannot see the source of the danger. But if they experience emotional contagion, they're going to start to freeze as well because they see that their buddies are being scared. And this means that now all the evolved responses to danger get used and deployed to save its life, even if it cannot directly sense the danger. So in a way, sharing the emotions of others can have a very selfish benefit, which is the fact that it allows you to adapt to dangers even before you can directly experience them. And I think as humans, we experience that in situations, for instance, there's a lot of examples of fire happening, where one person detects it, gets really scared, and this very rapidly kind of alerts a whole group to the danger. Everyone's adrenaline starts pumping up, and everyone is then really prepared to deal with that situation. So once the cat moves away, of course, one of them can directly notice that, can relax, And now through the other phenomenon that I explained you, the fact that you relax when you're around more relaxed people, now the animal that was freezing can get the social buffering, can relax, and now they can keep stealing my cheese. But I think what this suggests is that there might be a very selfish reason to care and share the emotions of others, which is as a way to sense the amount of threat that's in the environment by using other people as kind of antennas to detect safety or to detect danger. Now, it still leaves us with the question, though, of whether this system would actually motivate us to help. So, of course, what I've shown you with the example of the 2 mice in my kitchen, if that's the whole story, then if you see that Ukrainian boy, the thing you should be learning is that it's dangerous to go to Ukraine. It wouldn't necessarily mean that you get motivated to help. But nevertheless, we all know that we do feel this urge to try to do something for others if we can. So the question here is, would the same brain system that's involved for this emotional contagion also determine whether you are going to help someone else or not? So again, the first thing we did was to turn to our rats to see whether they actually care about what happens to others. So what we did here was an experiment where the observer becomes an active part of the experiment. What we do is we give them 2 levers and they can experiment. So they try the first lever, they see, well, this one is easy to press, and each time I press it, I get a delicious kind of sucrose pellet. Then they try the other one, they realize, gee, this one is at least twice as hard to press, and I also just get 1 sucrose pellet. So because they're a little bit lazy, most of them start to develop a strong preference for the easy lever. Now that they have a preference, we introduce something slightly demonic. Is that each time they go for the easy pellet, we give a little foot shock to the guy on the other side. If they use the hard lever, they get the same amount of food and nothing happens to the other one. So we figured if they're willing to do something for the benefit of others, we should see that they would be willing to switch, to work a little bit harder, but to prevent harm to others. And that's exactly what we observed. So both in males and in female rats, what we observed was that before we introduced the shocks, they have a strong preference for one of the 2 options. And once we start to pair that with adverse consequences for others, the preference disappears and they get to the 50% level. Now, we know that this is not just because they get bored with one of the levers, because if we kind of disconnect the shocks, they don't switch. And even if we administer the same number of shocks, but no longer at the moment where they press the easy lever, they also don't switch. So it's really about realizing the contingency between what I do and what this does to you here that seems to motivate the animal. Now what we see is that not all rats actually switch. So if we don't look at the group of rats overall, but at individual ones, we see that some of them, and this is about 1/3 of the animals, completely stop to use the easy lever. They really don't touch it at all anymore. But then we have about between 1/2 and 2/3 that don't switch at all. They just keep going for the easy lever, never mind what it does to the other. So this individual variability is something that we want to understand better, but we still don't know what it is exactly that makes them different. But this is really something that intrigues us. But now what we can ask is what would happen if we now deactivate the cingulate that we thought was important for sharing the emotional state of others? Would they still switch or not? And what we observe is that if you inject saline, that doesn't do anything. You see that they switch, that's the blue line. But if you deactivate the cingulate, they don't switch anymore. None of them cares anymore. So this is really the first empirical evidence that modulating this ability to share the pain of others and to map them onto your own pain is, at least in the rat, what seems to be motivating animals to prevent harm to others. Really giving arguments for what Smith was arguing, that the reason why we behave morally is because we don't like the way it makes us feel when we harm other individuals. Yes?
That's not what you've demonstrated yet. We're still talking about emotional contagion, not about pure empathy. So what you now have is that the rat gets a fear signal from the other rat, and it's now choosing for easy food without fear. So easy food with fear, or hard food without fear. And it's choosing for hard food without fear.
Can you repeat that? Because
yes.
Nobody heard that.
So I think if I understood your questions correctly, what you're saying is that what I have shown here is not that the rat really cares about the state of the other. What I've shown is that they avoid the state, perhaps, that it puts themselves when they shock the other one. And we think that this is perhaps exactly what is happening. So their motivation here might be that they don't like the way that it makes them feel when they shock the other animal. And actually, when you look at the human literature, there is a really nice work by Davis that shows that about half of humans seem to basically have the same motivation. And the way that he sees that is he made an experiment in which you would come to the lab, you would do something boring, then when you finish with that, on your way out, you would see that the other participant was submitted to a different condition that's about memory and where they have to get shocks each time they make a mistake. And the experimenter tells you, look, the other person seems to be really not taking this very well. Would you be willing to take some of the shocks for the other person? But now there's two groups. In one of the conditions they say, if you don't want to take them, it's not a problem. You just have to stay here and watch. And in that group, everyone seems to say, yeah, I can take on some of the shocks. In the other condition, they say, don't worry, you don't have to take them. If you'd rather, you can just go home. And there suddenly, about half of the people just choose the option to go home, suggesting that it wasn't really that they wanted to help that person, it's just that they really don't like the feeling of having to witness the distress of the other one. This is not to say that some of us may not have the more noble concern, and probably all of us have a bit of both of these motivations, where there's also the fact that we feel some moral obligation to help, even if we don't have to witness it directly. Yes?
The microphone here, please.
Is there a possibility that you can't identify what emotion the other animal or person is feeling if you can't feel it by yourself?
Yes.
So can you still know what they are feeling if you can't feel it?
So this is a really interesting question. There's two pieces of evidence in the literature that really relate to that. One is a patient that had a stroke in the insula, and what happened was that after the stroke, they did not feel disgust themselves anymore. So their husband was reporting that at some point they went on a vacation for 2 months, came back, and there was a carton of milk in the fridge that had been there for 2 months. You can imagine the state of the milk, right? But before the husband could check on the wife had gone to the fridge and had poured the clumps of rotten milk into a glass and had started to drink it. And the husband was really horrified, but she did not understand at all what was disgusting about it. But the interesting thing is, if you showed her a picture of a happy person, she could tell you, yeah, the person is happy. Can show her a sad person, she can tell you, yeah, the person is sad. But when you show her a picture of a disgusted person, she really can't tell you what that person is feeling. And she starts to say, I think the person is angry, which is something that none of the controls mistake discussed for that. So that's one example. Then there's another famous example of patient SM that had a calcification of the amygdala bilaterally, and that doesn't experience fear in most situations. And that person is also really bad at understanding when other people are scared. So those are the two best examples really of a dependence between knowing what it feels like and understanding it in others. And we think that's what happens in our rats before they ever experienced the foot shock before. Then they find it a lot more difficult to really react to another animal getting foot shocks with an appropriate emotional response as well. Yes? I think, yes, the microphone is here.
Thank you. I wanted to ask if there's maybe any evidence for if you suppress the ACC that the rat still feels the stress response, because I don't really understand why it is operationalized that the ACC stands for like fear detection, because it's also involved in a lot of other systems such as conflict monitoring, and at least in humans. I don't know how it is in rats, but wouldn't it make sense to also measure the stress response like skin conductance in humans? I don't know, again, what techniques exist for rats.
So I'm not sure I entirely understood the experiment that you want me to conduct. So you're saying kind of, should I lesion the cingulate in humans and check whether they would still have a galvanic skin response when they see the distress of someone else?
Yeah, it was more about rats, because you injected the muscimol in the
Yes.
ACC, right? But because the ACC is also responsible for conflict monitoring, maybe the rat just cannot attribute to why it is feeling an emotion and cannot react to it. But maybe it is feeling the emotion.
Yeah, so that's why we did the experiment of deactivating it and triggering fear through the fear condition tone. Because there we see that the rat still freezes, so it can still experience the emotion of fear and distress, but it's no longer able to recruit that feeling by witnessing another one in distress. So what about kind of humans? How would we deal with a situation like that, where we have a choice between an easy lever, so to speak, that gives us kind of money but shocks someone else, and another one that doesn't give us as much money but prevents shock to other? Well, that's an experiment we've done. So we give people two arbitrary symbols, and they can try to press one of the symbols. If they do that, they see they get 0.5 euros, and they have to witness how this other person gets a very weak shock on the hand that's not even really unpleasant. Then they try the other symbol, and they see that when they do that one, they get more money, which is good news, but they also see how the participant in the other room now gets a much more unpleasant shock on the hand. Now, which symbol will they keep pressing? Well, what we see is that with these amounts, so the difference is 1 euro, and for a shock to someone else, people really split into 3/3. 1/3 of the people decide to use the option that doesn't make them a lot of money, but prevent shock to the other. 1/3 actually goes for the option where they get the 1.5 euros and someone else gets a shock. And about 1/3 are in the middle here, where they switch between the two. So they make a bit of money and they save a bit of shocks to others. We thought that the distribution was really strikingly similar in a way to what we find in the rats as well. So kind of when we think about the moral nobility of the two species, I'm not sure that there's such a huge difference. But what is interesting, again, we can now as well look within the human brain to see what parts of the brain are really involved while you're learning from trial and error what is bad for other people. And we see that the same region that we saw to be causally involved in the rat is actually in humans as well, keeping track of the consequences that your actions have on other individuals. So again, showing a somewhat striking similarity both in the variability in the choices and in the brain system that are involved. Now this brings me to the final part of my talk, which is to ask us whether the system that we share with rats is something that's just always online, or whether it is something that we up and down regulate based on the decisions and situations that we're in. Now, what brought us to start to think about that was actually an experiment in which we studied psychopaths. So, so what you may know, certainly from Hollywood movies, is that certain people are really quite comfortable with causing a lot of distress to other people. And it's a group that is called psychopathic criminals. So what we've done here is we went into forensic high security institutions in which these psychopathic criminals are incarcerated, and we recruited 18 of them to take part in an experiment in the scanner. So these are really people that have done some seriously bad things, which involved either murder or really multiple, very violent rape. We compared them against people of the same age, same IQ, and what we did was, in the experiment we had two halves, like in many of our experiments. One half in which they simply witnessed the pain of other people, either physical here, or we also had here a more social pain condition in which we show one person that is being nice to another one, but then being roughly pushed away. Then in the second part of the experiment, our graduate student went into the scanner room and kind of whacked these criminals on their hands to cause them some pain and teach them a lesson. Or as well, these criminals had to try to caress her hands, and she would just push them away. Funnily enough, kind of the only condition that they thought was really quite triggering for them was this social exclusion condition. They really didn't like that one. But so the first thing we did was we looked in the brain to see whether one of the theories of psychopathy is true, which is the fact that they just don't feel emotions, they're completely cold. That's not what we found. So in these conditions where they got whacked on their hand or excluded, their brain activity looked indistinguishable from that of the normal participants. So they involved all of these brain regions we've talked about, like the premotor regions, the somatosensory regions, and the emotional regions like the insula and the cingulate. But what happened while they simply witnessed the pain of others? Well, then we saw that the controls had strong activity in all these regions, whereas they had really very weak activity in these regions. So here we figured, okay, now this is quite striking. So it looks like they basically are lacking this mirror system that transforms the pain of others into their own pain. And that's why they can do these terrible things. But then we figured, and in particular Valeria figured, well, so these are just all the differences. But she figured, well, does that really work? Because very often the victims said it was really weird. He was super nice while we were in the bar, and then afterwards we went to his apartment, and then he started to really treat me like an object. So that's not something that sounds like they're incapable of being empathic. So we figured, let's scan them again, but this time we'll ask them to try and empathize with the people in those movies. And when we did that, all the differences disappeared. When they want to be empathic, their brain activity looks like that of controls. So basically what we realized here was that perhaps what psychopathy is, it's not the inability to empathize when you want to, but it's basically a form of talent almost to turn off your empathy when you don't need it, and only to turn it on when it suits your purpose. So that is kind of the ideal brain makeup if you have a predatory lifestyle, because now while you try to convince the person to trust you, you can turn on your empathy, you really understand what she wants to hear, everything works fine. But then if your goal is now different, it's no longer to seduce but now to use, then you just turn it off, and suddenly you don't have all that guilt feeling that's in your way anymore. So this alerted us to the fact that perhaps our brain is not just that you're equipped with a certain level of empathy, and that's always the case, but at least they seem to be able to up and down regulate this. But then we figured, how about you and me? Do we have this ability as well? And actually there is an increasing amount of evidence to show that we can all do this. So the first experiments were experiments that Tanya Zinger did together with Cretin, where she, for instance, showed people someone in pain and told them, oh, and by the way, that person likes the same football team that you like. And then you see, gee, there's a lot of activity in my insula while I see your pain. And then you see someone else in pain, and you say, oh, and by the way, he likes this football team that you don't like at all. And that's enough to reduce the amount of activity here in the insula quite dramatically. In another set of experiments, we looked at the effect of responsibility. So here, for instance, you see the pain of someone, and you know that you caused that pain. Then you get the blue bar. The red bar is the same person getting the same pain, but this time it wasn't your fault, it was somebody else's fault. And there you see as well that you basically disengage your own pain sharing. And finally we figured, well, let's make it even simpler. We're just going to show people a Hollywood movie of someone's distress. This is the champ. And we're going to ask in one condition to tell me second by second how the kid feels, but to try to detach. Or in the second condition, you still need to rate what the person feels, but this time try to be empathic. And what we see is that this difference really turns on and off a lot of this empathy network significantly. Meaning that all of us, all of the time, we basically have a choice of how much we use this biological system that we share with rats. We can decide, I turn it on, I turn it off. We differ a little bit in how much we can do the on and off, with kind of psychopath being extremely talented at doing it, and some of us really not being very good at it, but all of us have the ability to do it a little bit. So stop thinking of empathy as something that you have or you don't. It's really something that you have a knob for. And I think it's important that we become aware of that so that we use that ability, that we turn it on really when it matters rather than leaving it dormant when you really shouldn't. Now, let's bring everything we've seen today to get back into the brain. And let's think now about what really happens in your brain while you witness this Ukrainian boy. What we've shown is that you don't just activate your visual brain regions that would allow you to see the boy. No, you also activate your own actions as if you'd be gaping yourself at that moment, your own sensations as if you were feeling tears rolling down your own cheeks, and your own emotions as if you'd be distressed in that moment. And with all of that activated in your brain, of course you no longer just understand and see what is happening to the other, but you start to really feel it, because in a way you stop to see that boy and you start to be that boy. Now I hope that by showing this combination of doing certain experiments in humans and others in rodents, we really get a deeper understanding of the system. Because I've been able to show you that if you deactivate this ability to recruit your own emotions, you basically stop to be really contagious by the emotions of others, and you stop to be really willing to work hard to help other individuals. We've also been able to zoom into these brain regions to see that we really have neurons that map the pain of others onto our own neurons. And something that I find really striking is that we share these systems with rats and with mice. That means that 80 million years of evolution have conserved this system, which I think has two sides to it. On the one hand, it really tells us that it's evolutionarily old and that it may therefore have a selfish aspect to it. And on the other, it really shows us that we are all equipped with a biological system that allows you to really relate to the emotions of others. And finally, I've shown you that you're able to up and down regulate this system. So there's some individual difference. If you're born a psychopath, your system is in a slightly different state than if you're not. But also that the situation and your own decision can turn this on and off. And that brings me to a last slide, which is a debate that some of you may have noticed in the literature. So for a while, people were really saying all the good things about empathy, and there are a lot of empirical evidence that being more empathic has good consequences. So we know that people that are more empathic are generally happier, more satisfied with their life. They have more friends, that's perhaps less surprising. They have more satisfaction in their couple, so it's nice. They commit less aggressive acts, so they bully less in school, for instance. They are better leaders, so in companies actually, being more empathic, really engaging with what your team feels, helps you to really be a better leader. They're certainly better doctors, and they are also more creative in groups, because if actually you work in a team and you try to listen to what other people say and really engage with what they're thinking, you manage to have better solutions. There is, though, increasingly also arguments for saying, well, empathy is not so good. And there's some good reasons for that as well. So the first problem with empathy is that I've shown you that it's biased, right? You empathize more with the people that like your football team than with the other one. And that's perhaps not what you would like justice to be, right? You shouldn't just do good things for the people you like and be bad for the other ones. The other thing, the problem with that biological system is that the activity when you see one person suffer is not 1,000 times less than if 1,000 people suffer, which means that for certain difficult decisions, this kind of system will make you privilege perhaps the outcome for one of your good friends rather than to take the decision that's better for the many people. Another aspect that is often criticized is the fact that imagine being a doctor and you feel the pain of each and every one of your patients. It might lead you to be really burning out, and therefore at the end you can't really help people because you're overwhelmed by their pain. So there's all these arguments with some people saying we should have more empathy, or others saying we should have less empathy because it does all these wrong things. So I hope that after my talk, and in particular the part about modulation, you would argue with these people to say that they have a simplistic view. Because the question is not, is empathy good or bad? The question is, when is empathy good? When is empathy bad? Because given that you can modulate it, you can get the best of both worlds. If you take control over it, you know to turn it on when you need it to be a better husband or to be a better doctor, but you can also then turn it down when you are at a point where you would otherwise risk to burn out. And I think what we need to do as individuals is develop that feeling of when we should really turn it on, and then really do turn it on, and understand as well when it gets in the way, and then develop good habits of knowing when to also down-regulate it. So I think at this point I'd really like to thank you for having spent your evening with me rather than with Netflix or with a good glass of wine. I'd like to really thank my wife, Valeria Gazzola, with whom I designed all of the experiments. We lead the lab together, and I wouldn't be here today without her. But there's also all of these amazing people that have helped in the animal experiments, and all these people that have helped in the human experiments, and the funders that make this work possible. Thank you for your attention.
So it kind of shows this picture that your empathetic brain is on. You're a good husband and you work together with lots of interesting other people and are probably good friends with them too. That's very nice. I would say just don't be fan of any football team. That might help to have some more questions, but you're first. Yes.
Thank you. Thank you for the lecture. So you talked about psychopaths and how they are very good at upregulating or downregulating those systems involved in empathizing. Do you have any idea why, at any level of analysis, genetics, molecular or network, why they're so effective at upregulating and downregulating those areas?
The short answer is no, unfortunately not. And that's part of why we're so excited about the fact that also in the rats we see this individual variability, where some of them really keep doing what hurts others and others really change. I think that gives us an opportunity to really try to better understand the difference between them, because currently, honestly, we don't.
Can I ask a second question? I was also wondering, if there's so much individual variability, do you think that that's actually an argument against why empathizing is so evolutionarily advantageous? Because wouldn't you expect most people to empathize a lot?
So that's really what I tried to introduce with the very last slide as well. Is it's not that empathy is the optimal state in all situations, or that no empathy is optimal in all situations. I think that there's different niche and different situation in which different levels of empathy are optimal. So this is usually the kind of situation in which you get really genetic variability. You can imagine when you're in a period of war, having the ability to be relatively unempathic becomes really the optimal adaptation. If you're in a very peaceful situation, where, because we're a human species, the most important thing is to be a reliable collaborator, actually being in a state where you pretty much always have your empathy on is the best strategy. But because we tend to have these fluctuations between periods of peace and war all the time, I think that what happened is that we just get variability in the gene pool, with some people having more of an always-on state, some with the more psychopathic phenotype, and everything in between.
Has research also been done on people with autism?
Yes.
And can you elaborate on that?
So kind of the two most studied groups when it comes to empathy is indeed autism and psychopathy. Psychopathy, because in prison it's a lot more difficult to do these experiments, so there's less studies there. But where you see the big difference is all I've talked to you about today is this relatively biological, emotional empathy. There is also something that we call cognitive empathy or perspective taking, which is your ability to think about the state of other people rather than to share them. And what we see is that in autistic individuals do not lack a sensitivity to the emotional state of others. So if you put them in a room with very anxious people, they get super nervous. If you put them in a room with very calm people, they stay a lot more calm. So the kind of systems that I've talked to you today, we measured people with autism in scanners with them, and they look pretty much normal in most of these systems, whilst the psychopath really show this abnormal thing. If, on the other hand, you give them tasks where they have to know what someone else is thinking you see that there the psychopaths are completely normal, and the people with autism struggle a lot more to actually deal with the fact that someone else can have thoughts that are dramatically different from your own.
Thank you.
Yes, many of the interesting traits that we get are traits that are useful in childhood and then originally would go away but then stick around. Now I can imagine that for mammals, they grow up looking at their parents to learn how to interact with the environment, that you sort of get empathy as a building block from there. Do we see that empathy decreases with age or anything like that in the literature?
No, not really. So in humans, there has been quite a bit of studies on the time course of empathy over the lifespan. What you see is that over the first 4 years of life, these phenomena really become more and more sophisticated. So in the very beginning, there's evidence that a baby will start to cry if there are around other babies that cry, even very early. So that's really the very simple emotional contagion. But over the first years of life, they start to develop more and more what I was calling kind of empathy proper, which is this ability to feel what the other one is feeling, but realizing that it's not you, and therefore starting to really help others. That develops around kind of 4 years, it becomes very reliable. But then afterwards, it stays pretty constant up to very old age. Well, up to the point where you get senile dementia. So there's certain variants, the frontotemporal variants of dementia, where then it goes down again. But up to that period, it's relatively homogeneous.
Yes.
Thank you for the lecture first. So I have two questions. First of all, was there literally just a difference in response to the brain activity in people who don't react on their empathy? Or was there a difference in brain activity in general for the people who, for example, always pressed the button that gave a large shock for the high amount of money?
So I'm not sure I fully understood. So what were you asking? Whether
was there a difference in brain activity between the people who chose to give the lesser shock and the people who give the stronger shock?
Yes. So we do see that. So within the network, we see that there's more anterior brain regions that calculate in a way the value of different options. Those regions were really very predictive of the decision that people were going to take. Whereas the most posterior parts, the visual cortex and for instance the insula, was responding to the pain of others within the normal population pretty much independently of whether you were going to help or not. So it looked like within the normal population, everyone was processing the pain of the other, but was attaching different values to it through a more valuation system. Once you get to the more extreme of the population, the psychopath, there you really see that even their response in the cingulate, in the insula, is really blunted when they witness the pain of others.
Right. Yeah, sure. So the second question is just a short one. Is there empathy to be seen across species as well? So
yes.
Yes.
Yes. So there's a whole field in ecology that is called eavesdropping, where they study the fact that if you're in the savannah and the birds get scared, the antelopes run away. So in a way, animals can really learn to be empathic if, let's say, to experience emotional contagion with members of a different species. So of course humans have that with their dogs in particular, but also I do, although you might doubt it, I do have a lot of empathy as well for the rats in my experiment, but it goes the other way as well. So there have been interesting experiments in which what people did was they gave shocks to humans, or not give shock, and then they ask the humans to hold a mouse in their hand. And they see that the people that got an electroshock and afterwards held a mouse in their hand were stressing the mouse, whereas the ones that didn't get the shock were not stressing the mouse. So even from human to the mice, there is a transmission of the state of anxiety.
Thank you for a wonderful lecture. I'm wondering, you use empathy the same as compassion? And if not, because it seems to me that can be the psychopaths, they have empathy, but we miss in the equation compassion, so feeling for the other, and not feeling the other. And I wonder if it's the last, is the results of your research is not going to change if you put in the equation compassion.
So there is some, there is an increasing amount of work that's not from my lab though, that tries to really distinguish empathy from compassion. And so the difference is kind of, if I see someone in pain, if what I'm experiencing is empathy, I'm really feeling something negative, a pain-like phenomenon. In compassion, what you foster is not a feeling of pain, but actually more of a warm attachment feeling, something that you normally have for your children, or so that you really want to protect them. And those two things depend or correlate with different brain networks. So people that report really negative feeling while they witness the pain of the other activate a lot the circuits that I was talking about today. People that actually distance themselves from the pain and get more this warm, compassionate feeling recruit other brain networks that are more striatal and medial prefrontal, that have been associated more with attachment and kind of both romantic and maternal attachment. So these two things are somewhat separable. I think in a lot of situations, they can flow one into the other. So sometimes your first reaction is the distress, and then you actually transform it into something else. So those are two different circuits, and I think what we see in the rat and human that I presented today is more really to do with really sharing the negative feeling rather than the more compassionate element.
Yeah, thank you. I have a question related to the previous question on across, like the empathy across species, more about non-animal species. So empathy towards, for example, plants. Some people really care about the house plants, but also about the environment and ecosystems in general. Why are there people that care about the environment and some that don't? So if you have some insights on this, maybe.
So what I think I've shown with the example of the football team, right? The fact that you're just kind of your belief that someone is part of your in-group or not, based on what football can really shift this. What we see is that applies as well to, for instance, the inanimate world. So we have made experiments in which, for instance, you see the actions of a robot rather than of a human. And we see that you recruit a lot of these systems as well in situations where there's a robot or even an object like a plant. And these individual differences, or also differences that you experience from one year to another based on how you've changed your attitude towards plants, for instance, I think reflect these mechanisms that we don't yet fully understand, that regulate the system on and off based as well on your beliefs and your attitudes. So I think we need to really understand that this is an old system, but one that we can, from 1 second to the other, kind of enlarge like a blanket to incorporate more people and more things, or really retract away from a lot of other people through this in-group, out-group difference.
Thank you for the lecture. I was just wondering, when you were talking about turning on and off the empathy, what do you mean by it? But are we still talking about electrochemical signals in the brain. So how would the turning on and off be different than reacting in a certain way to certain photos or certain people experiencing something that we would describe as, let's say, bad or something in that term?
So let me try to explain it through something that we might all be more familiar with, which is the fact that we regulate our own emotions. So for instance, when I write a paper and the reviewers tell me that it's terrible and that they reject it, my first reaction is I get incredibly angry. And then I realize this is not productive, so I downregulate my own anger. We know that in the brain this happens because you have prefrontal regions that have inhibitory connections to the more effective regions like the cingulate, the insula and the amygdala. So all of our brains are equipped with a lot of modulatory systems through which we can deliberately up and down regulate our own emotions. Now these systems, of course, because the emotions of others basically recruit my own affective systems, are still in place also when the source of what I'm feeling is not something that happens to me, but something that happens to you. So the idea is that, of course, you witness something, so your visual system represents there's someone in pain. This is sent onwards through connections to parts that are involved in your own pain. You recruit an emotional state, and then you have these inhibitory systems from your more cognitive prefrontal regions that can downregulate this system that is now being activated. Just like you regulate, I hope, your own emotions all the time.
Yes, I have a question regarding the ability to regulate empathy. What you also just talked about. So you talked about that psychopaths are very good at doing that. I was wondering whether there were any other major groups that sort of stood out in their ability to regulate this empathy. For example, I know that people with ADHD or depression have a hard time regulating emotions. So is this maybe also the case for regulating their empathy?
That is a good question. So I'm not aware of really good studies, for instance, that look at the case of depression. What we do know, though, is there's an increasing amount of studies that look at what happens in medical doctors. And if you scan them in the very beginning of their training and at the end of the medical training, you see that they've really developed the ability to downregulate their own pain sensitivity when they witness the pain of others. So there's, I think, a relatively deliberate training during your internship where your kind of mentors help you to downregulate your own distress. I don't necessarily think that this is the right way of doing it, because I don't think that we should teach them to just downregulate their empathy, because there's all those evidences that it's actually better for the patient if you're more empathic. I think what we need to teach them is really to be able to turn it on when it matters, and then to turn it off when it's no longer necessary for the patient but would be really bad for you. But that's not exactly your question, of course, but that's the answer I wanted to give.
You now talked mostly about visual stimuli. What's the case with when we hear something or have an audible stimuli or read in a paper about the war, or do we feel the same empathy as we do when we have a visual stimuli?
Yeah, so we've done these kind of experiments. So the first experiments we did were looking at sound. So in terms of the motor system in the beginning, what we did, for instance, is play someone back the sound of someone ripping paper, and you'd see that you will activate your own hand representation as if you'd be ripping something yourself. Whereas if you hear someone gurgling water in his mouth, you activate your mouth regions. For pain, what we've done in both the animal and in the humans is play back, for instance, the sound of someone screaming in pain. If you do that, that recruits these systems in both humans and in rodents. Of course, if you look at the whole brain activity, it looks different, right? So in the cingulate and in the insula that really code the affective state, they look very similar, vision and sound. But of course, the input to the system comes from different brain regions, visual or that. Now, the last part of your question is what happens when you just read about it. So we've done that less in the animals, but in the humans, we have done it. And you see that this is perfectly capable of inducing very strong activity in these visceral regions like the insula and the cingulate. So if you read something and you put yourself into the imagination that we all engage in when we read a good book, you see activity in these regions that looks at least as strong as what happens when you see the emotions of others.
Some more questions, but we have to finish. I thank you very much. I wonder if everybody has found their switch to turn on and off. I heard from you that by telling people to watch a movie in a certain way that they could get more empathetic. So I'm asking you to switch on your empathetic brain when you go outside in the world and meet others. Thank you very much, Christian Keizers. If there are any more questions, I'm sure he's not like running out. He's still here.
Exactly.
Thank you very much. Yeah, I'm sorry, we have to close. If you want a question, you can ask personally. Come forward. Christian Keizers is still here. Okay? Thank you very much. See you next time.
Thank you.